Hello, folks. So we will pick up where we left off, starting with Chapter 15. Chapter 15 is where we introduce the concept of equilibrium, or large K, which is different from little k. So we'll start off by talking about, in this video, what equilibrium actually is, and from there we'll move on to things of how can we determine it, real world data, and eventually moving on to more complicated situations, and finally Le Chatelier's principle, which is how can we physically manipulate K. So let's go ahead and get started. With that in mind, chemical equilibrium. Now, last chapter we studied kinetics, which was essentially how fast a reaction will proceed towards products. However, that kinetics doesn't always express how much products will be formed. Now, if a reaction goes to completion, their kinetics will go until the reactants are completely consumed. However, not all situations are ones where the products will completely form and all of the reactants will be consumed. There's some situations where we will only proceed partially to completion, some that we will proceed barely to completion. Just for example, when we talk about insoluble solids aren't truly not soluble, they are just poorly soluble. There is an equilibrium that is occurring where the solid is dissolving and the solid is the aqueous solution is recrystallizing. And it just so happens that the solid does very little dissolving. There's some trace amounts of it present, but not enough to really of any noticeable amount. So that's an example of equilibrium. So the example of these non-fully reaction states. So this brings us to a concept called equilibrium, which is the push-pull balance of reactants and products that will control the degree of chemical reaction we will see in many complicated systems. Equilibrium only truly works in reversible reactions. However, surprise, surprise, most reactions are technically reversible. It's just practically most of them don't. If some of them have a high product ratio or they have some sort of driving force that pushes them forward, they don't usually reverse very easily. But in a reversible reaction, there's a rate of forward reaction and there's a rate of reverse reaction. And equilibrium is the dynamic process by which, at a certain point, the forward reaction slows down because there's less reactants to react. And because there's more products, the reverse reaction speeds up. Eventually we get to a point, a balancing point, where there is no net change in products or reactants. The reaction still is occurring. Reactants are going to products, but for every reactant that's going to product, there's a product going back to reactant at the same time. So if they're going at the same speed, it doesn't matter that they're still working, you have no net change. So this is a very careful balance. Generally speaking, the forward reaction of this reaction, N2O4 breaks apart to NO2, 2 molecules of NO2. The forward reaction is simply defined as K1 times N2O4. It's a first order mechanism of N2O4 breaking apart. The reverse reaction has its own K constant, and it's a second order reaction of 2 NO2 molecules have to collide. Now, if we look at the molarity over time, we see NO2 coming in and N2O4 dropping out, but you don't see N2O4 dropping out to 0, we see a magical stopping point, an asymptote that's less than 0, where N2O4 stops at. Now, at the beginning, there is a lot of N2O4, very little NO2, and so the forward reaction is going to proceed quickly, and NO2 is going to grow in. But suddenly, as NO2 is growing in, the reverse reaction is going to start occurring more quickly. And so if we look at, instead of the concentration versus time, but instead the rate versus time, we'll see the rate of the forward reaction is fast and it slows down, and the rate of the reverse reaction is slow and speeds up to the point where they meet. When they meet, we're at equilibrium. Note the two rates are equal, not necessarily the concentrations. We're not going to go till there's 1 molar of each, but we will go till the rates are the same. That is what it means to be in equilibrium. Now, because the rate of the forward reaction and the rate of the reverse reaction are the same, we can set them equal to each other. And if we know how to measure the rates, we can set these expressions equal to each other. The K1 N2O4 equals K minus 1 NO2 squared. So separating these guys, the constants from the variables, the constants from the concentrations, you get products NO2 squared over reactants N2O4. And you get the constants K1 over K minus 1. Well, we're going to incorporate those two small k constants into a big K known as the equilibrium constant K. Now, from here on, for the rest of the semester, when we talk about K, we are going to be talking about this big K, not the rate constant K. This big K is going to keep coming up over and over again in many different ways. So we need to make sure we understand this very well. But it's simply looking at the rate constants for those two, the forward and the reverse expression. Here's the neat thing. It's a capital K because K is a state function. That K is independent of the mechanism. It doesn't matter how many steps it takes to get to products. We only care about the final step and the initial step, the reactants and the products. So it's different from the little k. K depends only on the overall chemical equation. So we don't need to know how it occurs, we just need to know what is the balanced chemical equation. The only way to change K, there is only one way to change K, and that is through temperature. A different mechanism, you put a catalyst, and K, big K, stays the same. Little k speeds up, but big K stays the same. A catalyst does not give you more products. A catalyst only ever gets you to equilibrium faster. Now, a reaction will always strive to approach equilibrium, regardless of whether we have more products or more reactants in equilibrium. But it only applies to truly reversible reactions. As I said, most reactions are reversible to some extent, so we're going to use the double arrows pretty much from now on. That the arrow going forward or the arrow going backwards. Now, there's sometimes some things that make reactions more reversible than others. Like, for example, if you produce a gas on a product side, the reaction is a lot less reversible because that gas can bubble off and it's hard for that gas to get back into solution and react. If you have a solid that precipitates, that tends to slow down reversibility. But if you have a bunch of gases reacting together, that in a mixture, that works very well. A bunch of aqueous together in a mixture, that works very well for equilibrium. So for a generic reaction of A and B go to C and D, we can write a K expression. The K is equal to the products, C and D, raised to their coefficients, all over the reactants, A and B, raised to their coefficients. And so notice the brackets that these are molarity values. Molarity values. Since concentrations are used, the compounds will only be expressed in molarity. But if we have pressures as gases, typically these pressures will be expressed in ATM. But with that in mind, molarity or ATM are the units we'll constantly use. Now here's the most important part. Solids and liquid compounds are never ever included in equilibrium expression. They are considered pure substance. They do not have a concentration that is capable of changing. It becomes very hard to deal with them. So with that in mind, if there's a solid in the formula, it gets removed entirely from the K expression. If you form a liquid, that gets removed from the K expression, and we simply ignore it. So now that we have a rough idea of how to determine K, what does K mean? What does it mean when K is very big, or what does it mean when K is very small? Since K is always a ratio of products over reactants, when K is very small, it means equilibrium lies to the left, that it's very reactant favored. There's very little amounts of products. And so in terms of reaction, you get very low yields, you get very low amounts of products. The reaction is not going to occur very much, if at all, when K is very, very small, like in 10 to the negative somethings. If K is very, very large, that means the reaction is very product favored. The equilibrium lies to the right. Means the reaction will go to near completion. You're going to get yields in the 99 to 100%-ish. That most strong acids have Ks of over 100, if not 1,000. So that we have almost 99% conversion. While many weak acids will have Ks like in the 10 to the negative fifths, sevenths, eighths, nines. So those don't break apart, while the strong acids do very much so break apart. And the last slide I'm going to leave you with here for today has to do with Kc versus Kp. There's two different Ks we will look at. The most common one we'll see is Kc. But we're going to have the Kc, by its idea, deals with concentrations, and Kp deals with gases, pressures. So when we have a Kp expression, it would be the pressure of NO2 over the pressure of N2O4, which is going to differ from the Kc, which would be the molarity. But in order to convert molarity into pressure, we have our Pv equals nRT. Well, molarity is N over V. So to convert a molarity into a pressure, you're going to multiply the molarity by RT. Now, R is a constant, and T should hypothetically be constant for a given situation, because the temperatures are going to be the same from product and reactant side. So in this case, if I'm converting the Kp into a Kc, I need to divide my pressure of NO2 by RT to get it into a molarity, and the pressure of N2O4 by RT to get into a molarity. Here's the thing, since I'm dividing both of them by RT, we can simplify, we can extract them. So you have 1 over RT squared divided by 1 over RT. So 1 over RT squared divided by 1 over RT cancels one of the 1 over RTs, but that leaves one of them behind. So whatever my Kp is, I'm going to divide it by RT, and that's going to give me my Kc. So we can write a generic expression that says Kp equals Kc times RT raised to the power of the difference in N. The difference in N is the total moles of gas. Total moles of gas. So if we look here, I have 2 moles on the right, 1 mole on the left, and so the difference is positive 1. But certain reactions might have 1 and 0, some reactions might be 3 and 2, some of them might be 3 and 1. So you could have a negative N, delta N, you could have a positive delta N. If they are the same, if you have 2 moles of gas on the left and 2 moles of gas on the right, delta N is 0. And if delta N is 0, you're raising R and T to the power of 0, which is equal to 1. So don't forget that we can do that. So we can convert Kp to Kc relatively easily, but it is not something we typically do very often, so we won't worry about it. But that's where I'm going to leave you for today. In the next video, we will look at how we can use some real-world data to find our Kc values. Have a good day.